Okay, so the viscosity is next. And as already mentioned in the introduction, this will be less significant in a modeling perspective. And it's a less significant because it's a type of the flow that is not common. It takes a place when the pressure difference through the orifice is moderate or is low. And that's typically not the case when we're looking at the mobile applications, and often also when we're looking at the industrial applications, is the pressure difference is very high. And that's, by the way, that's pretty much how the hydraulics operates. So it's based on the fact that it's introducing pressure losses, and those pressure losses have to be significant in order to introduce good controlling capabilities. So, but anyway, so let's take a look at the viscosity short. I'm not going to spend too much time in this because the next topic will be the utmost importance. So that will be clearly the most important matter in case of hydraulic modeling. And that's line fluid theory. That I would like you to understand back and forth. So it have to be completely clear for you. And what that is, that's we can open right after the introduction of viscosity. Now the viscosity, in order to understand that, I have an experiment. This time is different than in the case of bulk models. So I have a thin layer of oil, and top of the thin layer of oil, I have a plate. And the plate is the one that is shown here. So this is a plate, and the amount of the height of the layer of the oil is considered to be y here. Then this plate is actually moved with help of the force. So the force is imposed to plate, and because of the force, it actually reaches the constant velocity. Because the way that the fluid, Newtonian fluids, how they behaves, and so the velocity of the plate will be v here, and how the Newtonian fluids, how they behaves, they're gonna behave such the way that the fluid particles that are close to the plate, say right next to the plate here, they have roughly same velocity than the plane itself. Then there's another extreme, and another extreme what comes to velocity, the other fluid particles that are close to surface that is standing still. So this is a surface that is not moving anywhere. So now when I look at the particle right next to that surface, it will have roughly zero velocity. How is the velocity profiles between the particles between these two extremes? We can assume that to be linearly distributed. So they're gonna follow the profile like it is shown in the figure. So that's pretty much how the fluid behaves, and this gives us a definition of bulk, definition of viscosity. Now, in order to understand the viscosity, we have to compute how much force is needed in order to make this thing to happen. So here is my force that is imposed to plate. This is a plate cross-section area, and then this is a velocity, and then this is a thickness of the oil layer. So those are the parameters that I needed. And then comes one additional parameter. Additional parameter is the one that is, that is denoted here as a nu. Look at me. So I made that correctly once. Is it nu? You all happy? I don't know. I think it is nu. Okay, so anyway, so that's nu is that additional component that is coming into play. That's the one that is called absolute viscosity. That affects the forces that is needed in order to do this setup. And that's what we actually after in this explanation. Now, if we're going to use the definition of shear force, and this comes from the strength of material, without no further thinking, that we know that the shear force you can get by dividing force with the corresponding cross-section area. Using that definition, I can tell that the shear force is actually this absolute viscosity multiplied by velocity divided by thickness of the fluid layer. So that's pretty much what I need. And now this, all the fluid that are used in hydraulics, they behave according to this equation. In practical applications, the absolute viscosity is not typically used, but instead kinematic viscosity is used. And the kinematic viscosity you can get by defining that absolute viscosity by the density of the fluid. And that one is this kinematic viscosity. That's the one that is denoted as a, help me here. So what is this? You don't even know that by yourself. So why is it you're so critical against me if I don't know these letters? So yeah, that's good enough. So what was it? So it's so let's call this as it's not the V, but let's just call it V. Okay. So anyway, so that's kinematic viscosity. That's you can get from excuse me. Here, that's the absolute viscosity, and from that you can get the kinematic viscosity, like dividing that simply by density. Now, important thing is that viscosity, the SI units are centistrokes, and I'm sure that you never heard that before. Typically, the viscosity units that you're more familiar with are those units that are coming from Society of Automobile Engineering. So if you look at if you purchase the oil to your car, probably selection will be based on Society of Automotive Engineering. They have a relation to SI units, but the Society of Automotive Engineering is American society. In American society, I'm not sure if all the American societies, but at least this one, they want to make things complicated because the units are, what they are, length of the left leg and so on and so forth. Very hard to deal with. So this too is not something that is not based on the SI units. But using this relation table, you can get an idea what exactly they are. But viscosity is a problematic feature in terms of modeling. And it's problematic because it's a function of so many different features. That is particularly vulnerable for temperature. You know that because even your engine, your car engine, you shouldn't take all the power off when the engine is cold. What it means actually when the engine is cold means that when the oil is not warm enough, because the temperature of the oil affects to its features quite significantly. And this is an example that tells you how temperature will affect viscosity. This is explained in a logarithmic scale and is a significant effect. This is problematic, very, very difficult to account in a modeling of hydraulics, but the good thing is often we don't need to worry about that because again, this viscosity is needed only in a laminar flow, which we will get back. Now this tells how temperature and the pressure will affect the viscosity. The pressure too seems to have a significant effect because this too is in a logarithmic scale. And the pressure here, maybe the pressure is a little too high. I would say that the pressure we can find in hydraulics are something like this, 0 to, this is in a megapascal, so maybe this is quite unrealistically high pressure, but still the pressure too makes an effect. But the most importantly, the temperature makes a significant effect to viscosity. All right, so with that, let's move on and let's open this topic that is the most important topic in a discussion of hydraulics, and it's called lump fluid theory. This is what I would like you to focus on my talk only. So leave your mobile phone, leave your laptop, leave your tablet for a little while and listen to me, because it helps you a great deal to understand this concept. And I'm going to be brief. All right? Now, the lump fluid theory, that's the way we really going to carry out the modeling of hydraulic circuit. And it's going to be something that applies to, the hydraulic circuits well. And it's something that accounts pretty much all the significant factors you can find except the pressure waves. Sometimes there is a case that you have very fast say, direction valve that is connected to pipelines. Hoses are not that problematic, but the pipelines, and you may be able to close the direction valve rapidly, and that may affect that there is a pressure waves that start traveling back and forth in your pipelines. That we cannot account by using this technique. But other features that are flexibility that we can account using this technique, and is computationally very efficient and is very simple to use. That's what we're gonna learn next. What is this method? And the idea of this method is that we're gonna go ahead and we're gonna discreticize our hydraulic circuit within the volumes where we assume the pressure to be equally distributed. That you don't understand yet, but I'm gonna explain that in a second when I have an example in my follow-up slide. So we're gonna divide the hydraulic circuit within the volumes. Understand that much. How we're gonna do these divisions, that we're gonna practice number of times during today's lecture. Then once we're gonna do these divisions or discretization, then we're gonna create the differential equations to each one of these volumes. And these differential equations are the ones that are based on long fluid theories. So they will be first order differential equation that allows you to compute pressures in that particular volume any given time, right? That's how it goes. Now, then the different components are, well, they can be very exotic. Direction valves, pressure valves, flow valves. They could be something that is based on digital hydraulics. By the way, that's what I would like to explain to you. Digital hydraulics. Have you ever heard that before? Yeah, I don't mind. I'm still going to explain that to you. But because of why is that? Because if you look at the innovations and if you look at the developments in the hydraulics from last 40 years, the list of significant developments is very short, almost non-existent. Because still is based on the fact that you keep on producing energy to your system, and then by losing energy, you're controlling your system. That's the concept of the hydraulics. So you're producing the energy with help of engine and the pump. And then the energy goes to your system, and then you have different kind of valves. Each one of them will introduce into pressure losses, energy losses, another way. And now when you have these energy losses, then that's when you're controlling the system, and eventually you have all the controlling schemes. Then you're looking at how much pressure is in your actuator, which is a pump, a motor, or cylinder. That's how it works. Digital hydraulics is a little different concept because the idea is not to produce excessive amount of energy or system, but producing energy that is needed in a system, and then controlling that in a very clever way that we're gonna get back. That's going to be maybe next Tuesday. If not, then it's going to be Tuesday after that. But digital hydraulics will be something that is kind of a little bit a new area in hydraulics, and it seems to be very promising. If it's really going to be very promising, that's what we're going to learn later. But let's this time conclude that we have just pressure valves, direction valves, flow valves. Why? Because we want to control the system. Those will be introduced by simple throttles that are restricting the flow rates. That's the means of the modeling. Okay, example. This is now, maybe if there is one slide that is important, this is it. So take a close, put your full attention to this. This tells how you can discretize hydraulic circuit. Now this is very simple hydraulic circuit. This is a damper. And the damper that consists of a cylinder, that's a cylinder, and then the piston that is moving back and forth. So the piston consists of this body and this body, and now what I have in this piston are trillings. So there are trillings where the flow can travel back and forth between these two chambers. But the damper itself consists of two containers. Container that is associated to this area, and the container that is associated to area or volume below. How is it we can solve force associated with this damper? Well, we can use the long fluid theory, and the first thing we're going to do is that we're going to discretize this hydraulic circuit to volumes where the pressure is assumed to be equally distributed at any given time. Okay, so what it means. So I have pressure in this corner that is whatever numerical value. Let's say that this is 150 bar. And then I'm pressing the piston downwards. So is it reasonable to assume that the pressure in this particular location is also 150 bar? So this is yes or no. Now you need to do like, this is yes, this is no, this is, I don't know. So let's vote. Yes or no. Please play with me a little bit. Oh, thank you, thank you. Can I come and hug? Okay. So is it yes? You say yes. Others you say no. Others are saying no. So with the majority, most of the guys, what is that you're saying? No, yes, no. Okay, so it's like not no. Okay, think about it. So if okay, let's put it this way: that there is no drilling here, and I'm pressing the piston downwards. Can I assume that the pressure here is same than here? No. Yes, they are not same, because you know what's going to happen because of that force is that the pressure here will be higher than pressure here, right? Now, these drillings, if they are small enough, it's going to cause the same kind of effect. So if I'm going to take a hold of this piston here, I'm going to press it downwards. The pressure here will increase, pressure here will decrease. Then they will be coming to same after a little while, but in that moment you're pressing the piston, they will have a different values. And that's the way that the damper actually behaves, like it behaves. Okay, so we cannot assume them to be having the same pressure. So obviously I have two volumes that I have to look at this system. The one volume is the volume that is associated to this part of the piston, and the other one is this part of the piston. Those are the two volumes. I can assume, and it is a fair assumption, to say that the pressure that is located here is same than pressure located here. Why this is a fair assumption? Because there is no throttles, there is no pressure losses between these two locations, because there is no pressure losses. You got it? Is that a bit confusing? Okay, so what I will do then is that I'm going to create the differential equation that is associated to this volume, and then I'm going to create the differential equation associated to this volume. That's the primary concept of land fluid theory. Then there will be connection, and the connection will be a throttle. The throttle valve, which is in real life these drillings in this piston here, and then the flow will travel back and forth depending where is the highest pressure. Try to equalize the pressure difference. That's the role of the flow. So flow is trying to equalize the pressure difference, or is introduced because of the pressure difference, however you wanted to express it, but that's how it goes. So that's the main concept of land fluid theory. Now the remaining task that we have is that we have to create differential equations that tells you how is it that you can exactly compute these pressures in any given time, and that's it. That's pretty much it. And then you have to have the skill to divide your hydraulic circuit within the volumes where pressure is assumed to be equally distributed. Okay, fair enough. Here's another example. I need to make this a bit bigger that you can have a close look. So I have here, by the way, is it clear? Do you know what these drawing symbols, what they stand for? Good, good, because otherwise it's become a bit hard to follow what exactly I'm explaining here. So I have here hydraulic circuit where I'm assumed that there is a constant pressure source. Of course, there is in real life, there is no such thing like constant pressure source, because pressure is produced because of the motor and a pump. But let's just call that there is a pressure source where the pressure always remaining to constant. And that could be whatever value you want. Then I have here direction valve that consists of 4 ports, 3 different operation conditions. And it is magnetically operated like shown here, which is typical scenario 2. And then from direction valve, I have a hose or pipe connection to counterbalance valve, which is used in cranes often. And this is a counterbalance valve, excuse me, this one here. And then the counterbalance valve, there is again hose or pipe connection to cylinder. And another way, the piston rod side is connected directly to direction valve. So having the system like that, let's look how is that we can discretize these two volumes where the pressure can be assumed to be equally distributed. First, I have here this pressure source, which is called as a PP. Okay? Is it fair to assume that if the pressure source is having numerical value, say 100 bars, is this going to be 100 bars as well? No. 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 It cannot. Because, it's possible that, it's that the valve here is just a little bit open. The purpose of the valve here is introduce pressure differences. That's what it's doing. So it's reducing the pressure. It's reducing the pressure from 100 bar to something else. So we cannot assume that to be same. It's actually throttle where the size of the throttle is adjustable. That's what this kind of valve is doing for you. Yeah, you want to argue against. Go ahead.
I'm not sure, but isn't it just a direction control valve?
Direction, this is a direction, yeah, this is a direction control valve.
So why would that act like a check valve?
Okay, so you still doubt, like, is it fair to assume that the pressure here is 100 bar? That's what you're wondering. Because the way it is operated, and this is a kind of, that's coming a bit later. It is based on the fact that there is a spool, and the spool is restricting the flow. So it's restricting the flow, and is introducing the pressure differences. Roughly speaking, that's what this kind of direction valve is doing for you. Now, that's the only justification that I have today. Sorry about that. I have the explanation, but it's really down here. It really takes a while to go and check it out. But can you please remind me that I will get back to this next week? So obviously, you just need to trust me. Can you trust me?
Yes.
Thank you. Okay, so you trust me. So what about others? Hell no. Okay, please trust me. I will get back to that. But the direction valve is introducing the pressure difference. But now, the next question is it all right to assume that, in this pipeline, the pressure here is same than pressure here, having whatever numerical value at any given time? Is it roughly same?
Yes.
Yes, it's roughly same. Let's say that, we have a 100 bar pressure source. This could be 80 bars, like this. Then, can we assume that here too is 80 bars? Well, maybe you're not familiar with this component, this counterbalance valve, but it can be closed. It can be closed like shown in a figure. It can be open, but because it can be closed, it can be possible that the pressure here is not at all the same than here. So we cannot make an assumption that the pressure here is equal than here. But it's different. It's different. Okay, summary. We have here pressure source. Let me change the color to make this clear, because this is, how can I change the color there? Here. Okay, we have here first the pressure source. That's the one here. Then we have here throttle, that is a adjustable throttle. That's the definition of, or that's in real life, direction valve. Then I have here this pressure, which is associated to this pipeline or hose line, that's the one where I can assume pressure to be equally distributed. Then I have here again throttle that is adjustable. What's that is in a real life? That's this counterbalance valve. And then I have here one more volume, this one here, which is the one that is computed here. You got it? What about piston rod line? The line that is associated to the piston rod side. You know, I have pressure here. Can I assume that the pressure here is roughly same than here and here? Of course, depends on the hose connection, but yes, I can assume that to be same, roughly same. So I only need one volume to compute this piston rod side, and then it's going to be connected to tank if the direction valve is having this operation condition. Clear? Now it comes to difficulty. I don't expect that the success rate goes really high, but I have similar system. So let me put this on. Similar system, but with the difference that I have not two-way cylinder, but the one-way cylinder. Cylinder is only having the pressure in piston side. There's no pressure in a piston rod side. Okay? And it's controlled by direction valve, and the direction valve is having this operation condition. Hold on, this is too small. So then I have different options. How is that you can define volumes in this case? Which one is correct? So this is associated to, this is pretty much exactly same in the previous case. This is the one that I have pressure source and then two volumes. This is a pressure source and just the one volume. And this is a pressure source and three volumes. Which is correct? Let me put this on. So next. In lump fluid theory, hydraulic system below can be modeled as, and the options are again here. Is this too difficult? Too simple? Would you like to go and would you like to get more hints?
Yes.
Okay. Yes, sir.
Only in this state, not in like shifted.
Yes, very awesome question. Awesome question. Can I come and hug? Not today. Okay, so end of the course, of course. Okay, so then, you know, look at that. I have this direction valve, and now the question is associated with the fact that the direction valve is having this operation condition, not anything else except this operation condition. And what it means? Okay, what it means that in this operation condition, the pressure source is connected to this one-way cylinder. So first thing is that clearly we have no connection from piston rod side to tank. So you can, you know, you got the hint. Okay, so that's off the question. So it's not for us because we have one-way cylinder, not two-way cylinder. Okay, then what it left is, you got my hint. So this is a bit ridiculous. Anyway, so then we have pressure source in each one of these options. Now it's just a matter, oh, hold on. In these options, which is the one that this can be modeled? You got it? Can you, okay, so all goes down to this question. Can you assume that the pressure here is same than in a pressure here, 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 and here, and here, all the way in this pipeline? This is exactly what we discussed in a previous case. And then we concluded that, yes, that's what we concluded. Now this is a great advantage for online participants, because I think at online participants, they can go back in the video. Can they? Okay, so they can go back and see what is that we discussed. Too complicated in my mind. Okay, So let me take a look. Okay, so we still need some time. And then we have 9 minutes left. And during that 9 minutes, I'm going to explain how is that you can define that differential equation that gives you the pressure at any given time. But I'm still expecting some 26 students to enter the answer. You guys all done? Okay. You sure you're all done? But online participants, I don't think they hear you, so what is the correct answer? Yeah, I'm not going to repeat that because they hear me, they don't hear you. Okay? But that's what it is. Okay, so 15 students are still thinking. So soon we are done. Let me give you a little bit extra time, and during that extra time, I will open this discussion. And this discussion is, how is that you can get this first order differential equation? Okay, I have another setup. So this is the final setup for today. So in this setup, I have volume. You know, the volume is the one that is shown here. So it's like having a little bit of the hose shape. And then within this volume, I have mass and the mass rate. And the mass rate can be considered as a density of the fluid within this control volume and the flow rate that is traveling within this volume. Now there is a certain mass rate that is coming in and leaving out from this control volume. And that's defined in such the way that the mass flow in is going to be density of the material that is coming in, and that's corresponding flow rate. And the density of the material leaving out and the corresponding flow rate. So that's my setup. And now what I'm going to start looking at is that I'll start looking at how the mass within the control volume can change. Well, that's very obvious, because if there is more material coming in than leaving out, then the mass will increase. Another way around, if more leaving than coming in, it will decrease. Okay, that's what I'm going to take a look at. So, and how is the mass then? Well, the mass is actually, well, that's what we learned already in a multi-body system dynamics. So it's a density multiplied by volume. So that's the control volume that I'm looking at. Now, this mass difference can be expressed such the way that difference in the mass is relation between incoming and outgoing the mass flow rate. If they having the same value, the mass will be same, will be constant. And like just that I explained, if this is higher than this, it will increase. Another way around, it can decrease. That's pretty much the equation that I need here. And what follows is a little bit of mathematical manipulation, but not serious. This is not going to be very bad, but simple to follow. But you got the concept so far. You sure? Clear? Absolutely clear? Keep that in your head, because I would like to show you something nice, and then we will continue. Something nice is, I would like you to see how the 100% look like. What? So that was not the joke, that's the serious thing. Okay, so 100% look like this. Oh, I made a mistake. Okay. So let me go and take a look. Was there a mistake in this thing? No, there was no mistake. Okay. So there was let me go back to the results. 77. I'm, to be honest, I'm a little bit disappointed. Because, you know, first of all, we agreed that this is not an option. This is not the good option to select. And some of you already you select that too. Because that's why this is not the good selection, because there is no hose line from the piston rod side. So that's completely out of the question. It left 3 choices. And now it's all like how many volumes we need in order to model it. And we concluded that we can assume that the pressure here, let me change the color again. Or not. Okay, let's not change the color. But let's explain that the pressure here can be assumed to be same than here, 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 and here. So it gives us one volume that is needed. Simply, it's only that you need. You just need to have this one. So it's one differential equation that is associated to this volume is enough to solve the response of this simple hydraulic circuit. One differential equation only. Okay, so then we're gonna go back to this explanation. So you're still with me, so you agree that the mass can change only if there is a difference in the mass, this mass flow in and out. Okay? Now, let's use the definition of mass and let's put that to this equation. Let's call not the mass flow, but the definition that was in the figure. So it's a density and corresponding volume in, density and corresponding volume out. All right? Now, this is pretty much still the same equation we discussed. Now I can actually carry out this differential operation, so I can differentiate first density and then the volume with respect to time, and that's what I'm gonna get. So here is my density with respect to time, and here's my volume with respect to time. Here is still a mass flow in and out. No difference in that. Now, if we're gonna assume that the density of ingoing and outgoing fluid is gonna be same, if it is same material, more or less same material with the same density that is coming in and going out, it simplifies my equation and I can write my equation as it is shown here. And look at that. So I'm getting close to be able to express my pressure. I'm gonna actually go ahead and manipulate this component, and then I'm good. I'm done with the job. Now, this is a little bit complicated thing, but this is coming from the chain rule of differentiation. In chain rule of differentiation, I think I needed to mathematics to explain it. So it's saying this equation, this is density, is minus. So this is coming from the chain rule of differentiation, this relation. And I'm going to use this relation with help of definition of bulk modulus. Now, using these two definitions, I'm able to express this time difference with respect to density such the way that is turned out to be pressure difference with respect to time. What is that? That's equal than the P dot. And now the P dot is something that we can use to solve the pressure any given time. It's same than, remember, in a multi-body system dynamics, we look at the x dot dot. And from that we can get x dot, and from that we can get x. Same here, except that's where we're gonna get started. So we're gonna get started from the P dot, and we're gonna get P. And what's P? Pressure. Why we wanna have a pressure? Because the pressure tells us how much force is produced by cylinder or a motor. Okay, so let's finalize the case. Let's take everything to right hand side of the equation, and once I do that, this is how my P dot look like. Now, look at the components what I have. I promise to leave it this time, but can I break my promise? Okay, thank you. I will compensate that next life. Okay, yeah, later, maybe later then. Later, I will give a simple written exam. Okay, now look what I have in my equation here. I have here P dot, and I have one more in-class quiz. I'm asking what is the thing that I'm ignoring in the method. Remember the land fluid theory, we are not accounting the pressure weights. But other stuff that I have here effective bulk modulus, which is associated to flexibility. It is accounted in the equation. Then the volume size, of course, that is accounted as well. Flow rate in, flow rate out is accounted. And the change of the volume, all those are included. And this is an equation that I'm going to repeat over and over again. That's what we're going to use in order to solve the responses from hydraulics. Now, my in-class quiz, final one, is this. Land fluid theory ignores, not accounting, pressure waves. What? This is called teaching. Or cheating, I don't know what it is called. Then change of the size of the hydraulic volume, physical size of the hydraulic volume, compressibility of hydraulic volume, and let me go and, okay, go ahead, shoot it. And that's it. Then that's what we're gonna close. Okay? So once you're done, you're good to go. See you on, what was it again? Tuesday. And then I need to get back to you with your direction valve. Okay, so what would you like to see? So you don't want to see this. 18 students. So sometimes what happens is that once you lock in,
This time it can be 100.
you think so?
Yeah.
I don't think so, because this is, we'll see. 13 students are still thinking. I think it would be a good idea to close this early, like just to give you like few seconds here to enter your answer. Then only the outstanding student will have the time to do it. And others that are not listening to me, they don't have the chance. Okay, let me put my camera ready, so I'm gonna take a selfie with 100%. What? You don't think that is gonna happen? Okay, so are we ready? So 11 students, you all done. Seems that it's, the numbers are no longer changing. So I can close the case. All right. So this is a moment of truth. 93. Very high, but not the highest. You know, the bad news is this. You know, the chance is to get thinner and thinner. We don't have that many in-class quizzes to go. Thank you, and see you on Tuesday. Was it this place or someplace else?
According to time, it should be this place.
Good. I like this place. I started to like this place, even though the other room is weak. It still is all right. Okay. Take it easy, and see you on Tuesday.